Start. So today we are going to talk about 3D rotations and velocity. So this will lead to kinematics, dynamics, and eventually legged robotics in 3D. Okay, so far we've only focused on 2D, right? So we've looked at rotations like this. So there's an x-axis, y-axis, and that's the global frame. And then we rotate about, let's say, an angle of psi to lead to a new axis x1. And so this is new y1. Okay, so this looks like it's rotation there is a rotation matrix which we wrote down as cosine psi minus sine psi, cosine psi. Okay, so though I said this is 2D rotation, really all rotations are in 3D. So really what we were drawing here was this picture, x0, y0, x1, y1, and clearly the axes were something like this. This was z, and we were viewing the entire setup from the z-axis, and so it looked in the plane, but this is what is really going on. It is basically a three-dimensional rotation, just rotation about the x-axis or the z-axis. Okay, and so the way we write this in 3D is we have a 3 by 3 matrix, so it will be cosine psi minus sine psi, cosine psi, and then there'll be 0, 0, 1, 0, 0. This indicates that the rotation is about the z-axis. So this is our 3D rotation matrix. And that's the 2D one, the difference being that just add a third row and put one in the appropriate place. So this is what I would call RZ. And the way we'll write this is a rotation by an angle psi. So I'll write it as RZ, the function of psi, equals R10. Now, similar to this rotation about the z-axis, you can define a rotation about the y-axis. And I like to use theta for y-axis. In this case, what will happen is there will be a 1 right in the middle. And then the other elements which are non-zero are the off-diagonal elements. That those would be, sorry, not the off-diagonal, but the elements involving the rows x and z. So that would be something like this: cosine theta, sine theta, minus sine theta, cosine theta. And this, by the way, the sign is correct. It is minus here instead of being a minus on the row 1, column 3. Okay. And then there is Rx, and that angle is, I like to use phi for x-axis, and that's going to have a 1 right in row 1, column 1. And then we would have cosine phi minus sine phi, cosine phi. So those are the 3 rotations about the x, y, and z axis. So now in general, so these are just rotations about one of the axes. So when we want to represent movement in 3 dimensions, okay, rotation about all axes, or the object can go multiple rotations, right? And when we have multiple rotation, the matrix which we'll get will not be quite the one I showed you with the 1 and zeros in the way I wrote down. It will be more generically written as R, like this form: R21, R22, R23, R31, R32, R33. So this matrix is not sparse, but by that I mean there are no zeros, and there's no reason to believe there'll be zeros, but it will be something like this. So we see that this matrix has 9 numbers, right? The 9 numbers are the 9 elements of a 3 by 3 matrix. Now, there is a property of the rotation matrix which helps us to reduce these numbers. So we have this property, which is that the rotation matrix is always orthogonal. Okay, so that means that if you take R transpose R or R times R transpose, you get an identity matrix. So I is identity, which means that it is equal to 1 0 0 0 1 0 0 0 1. Okay, so that's a property of a rotation matrix, and the intuitive reason is that a rotation matrix can only rotate an object, cannot scale it, and that's why you need it to be orthonormal. Otherwise, it will not only rotate but also scale things. Now, this condition actually imposes some restrictions on these r's, the small r's I wrote down, and those conditions are the following. So summation ri1 square equals 1. So here I will go to 1, 2, and 3. What that means is if you take R11 square, R12 21 square, R31 square, you should get 1. Okay, so that will be this column. That comes only because of this identity. Is that right? Hold on, let me check this. So maybe we can expand it to make more sense of it. R11 square plus R21 square plus R31 square equal to 1. Okay, yeah, okay, so any column, if you take that, should sum, the square of the sum should be equal to 1. That's right. And then we have similarly R square I2 equals 1, where I goes from 1 to 3. And similarly I3 square, where I goes from 1 to 3, should also be equal to 1. So you can write similar expressions for these things, but that means that if you take any column and then you take the sum of squares, that should add up to 1. Okay, so then there's another condition, which basically is that if you multiply corresponding columns together, then the sum of the product would be equal to 0, and that is best written as this: Ri1 Ri2 equals 0, where I goes from 1, 2, and 3. So we can expand one of them up. It's Ri12 Ri11 Ri12 plus R21 R22 plus R31 R32 equals 0. So let's see what that means. So if I do R11 times R12, R1 times R12, R21 times R22, and R31 times R32, then the sum is equal to 0. That is just saying that the two columns are orthonormal, because if you take the product or dot product, you should get a 0. And so similarly, we can write Ri2 Ri3 equals 0, where I goes from 1, 2, and 3, and then summation I3 I1 equals 0, where I goes 1, 2, and 3. And so what we see is that there are 3 conditions. So we have 9 numbers, right? 9 numbers corresponds to the R's, but there are 6 constraints, which means that, so think of those constraints as equations which these R's have to satisfy. So if you have 9 numbers and 6 constraints, you're left with 3. So there are 3 unique numbers, which means that rotation matrix doesn't have 9 numbers which need to be defined. You only need 3 numbers in order to define a rotation, okay, in 3 dimension, which we have many choices, which I'll talk about later, but it's not so complex as it looks. It's only 3 numbers which define a rotation matrix. So how can we define a rotation matrix? Where the one way we do it, and there are infinitely many ways, as you see, the way we do it typically is we think about rotations about the x, y, and z axis, or x, y, x axis, and so on. You could in fact have rotations about 45 degrees about the x, y, and 45 degrees about y, z, but people normally don't take that because that's more complex. So here are the common ways of representing. So maybe I should make a note here. So we only need 3 numbers to describe 3D rotations. Okay, so 2D rotations, we only need 1 number, but 3D rotations, we need 3 numbers. Now, what are the ways? Some of the ways to represent rotations. Okay, so what we are doing here is we're going to think of rotations about the x-axis, then y-axis, then z-axis, x-axis, y-axis, followed by just x-axis, then z-axis, then y-axis. Then we would have x-axis, y-axis, then x-axis, and so that, by the way, is unique. X-axis, z-axis, and x-axis. So this is 4 combinations where x, the first rotation is about x. Then we could have start with y. We could have y, x, z, y, z, x, y, x, y, y, z, y. So those are 4 with starting off with y. Then we have z, x, y, z, y, x, z, y, z, z, x, z. So we have 12 combinations. As I said, these are just some of the ways we can do rotations. These, the way we do this is known as actually Euler angles. Okay, there are 3 angles used to describe the rotation about the rotation of an object in 3-dimensional space. Okay, now not all of them are used. There are preferences, like for example, we'll use 2 of them in this course. And really, you can use any notation you want. It's like, how do you call an apple in English or Spanish? It's the same thing, object after all. So rotations by themselves are the same, but there are different ways of capturing them. So you could either of them and you'll get the same answer even in the end. So the ones which we will be using in the class for some part is this combination. It's called this one is called are known as the Bryant angles. When you have 1, 2, 3, it's also called as 1, 2, 3, indicating that it's rotation about x, y, z. And the other one which people prefer is the zyx, and I don't know if that has a name. It's 3 to 1. Maybe it's the Tate-Bryan angles. I'm not sure. So I think that in when you do aerospace, they typically use the 3 to 1, or maybe it's 1 to 3, I forget. But this is, so every field has its own way of using one of these conventions. But it's not really that important name or anything, but you just have to stick to one and use it. Okay, so as I said, there are 12 combinations, but 12 ways to represent, but we only will stick to use these 2. Okay, and if you understand it for one, it's very easy to do it for others. Now, the other thing which I think is kind of very important, that rotations in 2D are commutative. So if you do rotation about by an angle psi 1, say about the z-axis, so we say cosine psi cosine psi 1 minus sine psi 1, sine psi 1, cosine psi 1, right? And then we have another rotation, cosine psi 1, psi 2, sorry, minus sine psi 2, sine psi 2, cosine psi 2. Okay, so we have 2 rotations, and what that means is we are rotating about the x-axis by psi 1, right, and then x-axis by different angle psi 2. Now, if you do this rotation such that you do 2 rotations simultaneously, so psi 1 followed by psi 2, you'll end up with this formula, which will be basically replacing psi 1 with psi 2. Okay, so I basically summed it up, right? So psi1 plus psi2, because if you do this rotation, it's obvious. If you look at the figure, you'll see that if you do psi1 plus psi2, then you'll end up with an angle which is the sum of the two. The other way of looking at this is, if you do this rotation successively, then you'll have r psi1 times r psi2. Okay, if you do this, then you'll see that is the same as the same thing I wrote here, which is also, by the way, the same which you'll get if you change the order of rotation. So if you change it to psi2 followed by psi1, then also you'll get. So you can actually take this R matrix and this R matrix and multiply them, and you will see that it actually boils down to psi1 plus psi2. So the commutativity is basically this. This is what is meant by being commutative. It's basically saying A times B is same as B times A. So R psi1 times R psi2 equals R psi2 times R psi1. So that's true for 2 dimensions. Now in 3 dimensions, however, multiplication is not commutative. So rotations in 3D are not commutative. Okay, so the easiest way to see this is, instead of proving it, is to actually do an example. So here is an example. So let's take an object which has dimensions which are different along the 3 axes. Okay, so this is a cuboid. It has different dimensions along the x. This is our x. This is our y. And then z has to be orthogonal by the right-hand rule. Okay, so now here let's do 2 rotations, one about the x-axis, one about the y-axis. Okay, and see what happens. So let's rotate this thing by 90 degrees about x-axis. Okay, so that means that I need to rotate. Okay, and then and this has to be counterclockwise. So when you see it from here, it should be counterclockwise, and this is this direction which will be counterclockwise. So if I rotate it by 90 degrees, I'll end up in this configuration. Okay, and since x is about which I rotate, x-axis won't change, it will remain the same. But the z-axis there'll be a new z-axis. It's called that z prime, and there'll be a new y-axis which will be upward. So y was to the left, it went up, and z was up, it went to the right, as you can see. Okay, so that's 90 degrees about the x-axis. Now let's rotate by 90 degrees about. So when we talk about rotations, there are 2 ways we can do it. One is we can talk about rotations about the reference configuration, or so in that case, if you do 90 degrees about y-axis, it would be rotation about this axis. But the convention we'll stick to is, instead of, and this is actually pretty confusing, so instead of that, we'll stick to the convention that we are going to do 90 degrees about the new y-axis. So in this case, it will be 90 degrees about new y-axis, which is basically the y prime axis. Okay, so again, when you do this rotation, you want to look at the positive direction and then turn counterclockwise as you would see it from top. So if you do that rotation, you can see that it will turn such that you'll have this. Okay, so since we turned about the y-axis, y prime axis, that will remain unchanged. Now the x-axis will orient this way. That will be x double dash because it's the second rotation. And then z is going to go this way. So what you can observe here is that the x, y, and z angles directions are changing. However, what you see is that z is always going to be at right angles to this larger, the biggest face. Okay, and then y is always going to be at right angles to the second biggest face, and then x is always perpendicular to the smallest face. So that is what is known as, this is known as the body frame. So x, y, z, or x, y prime, z prime, and then x double prime, y prime, z double prime are all body frames. And you can see that the body frame, even though those are named as primes, those are still sticking in the same direction. So the body frame, the XYZ maintains its orientation about the body frame. Okay. However, those X, Y, and Z prime are changing their orientation with respect to the world frame. And the world frame is this. The world frame is the frame we start off with. So now Z, for example, is Z double prime is in a different direction than Z was. It's actually along the X direction. Okay, so that's an aside. So we'll continue this. So we did 90 degrees about X, 90 degrees about Y. Now let's do this differently. Let's first rotate 90 degrees about y-axis. Okay, so when I'm doing this rotation, I need to look at it from here, and then I'll be counterclockwise as you look from that side. And so when you see that, it will actually be, I think it will be this way. The larger face looks like it should be here. Okay, so the y will be unchanged. So that's where it will be. The z is going to stick to the right side, so z prime. And then x will be, I think it'll be down. My bad. It will be pointing downwards. So I'll be prime. So 90 degrees about y-axis. And now we'll do the final rotation, which is 90 degrees about the new x-axis. So that will be x prime. So again, when you're doing it, you need to observe this from here. And then you'll see that it's to be done this way. And so if you turn it along the x prime axis, then you see that this object would be oriented this way, where x will remain unchanged, it's x prime, and then y would have gone that way. So 90 degrees to this y, and then z would go this way. Okay, so what I've done is I have done these two rotations, 90 about x, 90 about y. So x, y. Then I did 90 about y, 90 about x prime. So I reversed the operations, and I see that the final configurations are different. So these are different, right? They don't look the same, which means that rotations are in 3D are not commutative. However, they are commutative in 2D. Okay, and so that's like the important message. So if you do rotation about x, rotation about y, that's not the same as rotation about x and then rotation about y. So, however, if you do it in 2D, as I showed you earlier, the rotations are commutative. Okay. Okay, so let's focus on the 3, 2, 1 Euler angles and see how to write rotations when we do Euler, when we use 3 to 1 Euler rotation. So let's do that next. So next thing is 3 to 1 Euler angles. Okay, so what is 3 to 1 Euler angle? It's basically z, y, x, and I like to use always psi about the z, theta about y, and phi about x. So if you don't remember, it's psi, theta, and phi about x, y, z. Phi theta xi about x, y, z. Okay, So let's do this now. So here is one way of showing this instead of using cuboids, which I think are sometimes are really hard. So X, Y, and Z. And so first, let's do a rotation about the Z axis by an angle of psi. And again, when you're doing the rotations, they're counterclockwise about the positive Z axis. So when you do that rotation, you will see that X would move and it'll go here. Y would rotate, it'll go here. And this angle is psi. And this angle is going to be psi. So that's Y prime. Okay, so what I'm going to do now is, so if you do this rotation, then, and if there's a vector, let's say C0, and this is your base frame. So 0 corresponds to the reference configuration, which is X, Y, Z. Then that vector will undergo rotation to C1. And we can basically write the equation relating C0 and C1. So if C0 equals R, Z, psi, C1, what this rotation matrix saying, and this is actually pretty confusing to people. The confusion is why is C0 on the left side, why it's not on the right side. And the reason is because think of, this is the body frame. This is the world frame. So what this rotation psi is telling you is that if you take the object in frame 1, okay, it's in body frame, and then apply the transformation, then you'll get the coordinates of that object in the world frame. So this rotation, by the way, is correct. It's not the other way around. Don't exchange C1, C0, even though it looks like you should actually exchange it the way I've drawn it. Okay, so this is how you write the transformation from C0 to C1. So now we can just do this process again. So what I'm going to do next is draw the new X prime, which is shown here, the new Y prime, which is shown there, and then keep the Z, right? So Z is same. Okay, now let's do a rotation about theta, by an angle theta about the Y axis. Again, you need to go counterclockwise about the Y axis. Okay, and so this is really hard to draw. So when you rotate it, Y-axis will remain unchanged. However, X-axis will rotate. And as I said, this is may not be meaningful, but I need to draw it changing a little bit. It's hard to draw in 2D, but this is going to be theta. So it'll be theta about the previous axis, so Z. So I need to call it Z double prime corresponding to the second rotation. So now what we can say is we have a similar expression. So we have C1, which is in frame, it's in this frame, equals, so this is undergoing a transformation to C2. And then the formula which relates C1 to C2 is R Y angle theta C2. So this is again the same way you interpret it, which is the object body frame is C2, and then this is telling you what it would be in intermediate frame C1. Okay, and then we can do that again. Do this again about X-axis. So in this case, it will be X double dash, and we would have C2 transforming to C3. And then we can write C2 equals Rx phi C3. Okay, so we have this expression, and this one. So 1, 2, and 3. So from 1, 2, and 3, what we need to do is we need to sub in C1 from here and C2 from here to here, and we'll end up with one expression which relates C0 all the way to C3. So we'll have R, Z, psi, R, Y, theta, R, X, phi is C3. And that's our formula. That's how we can relate what is the relation between the body frame and the world frame. So this is okay. So there are many ways to interpret this. The one which I really like is the fact that I like to think of this as the body frame. And this is the world frame. So what it means is if there's an object, like so, and then let's say that X is like this, Y is like this, and then Z has to point out this way. Okay, so this object is initially in this configuration. This is in C0. So then it undergoes it undergoes 3 rotations. When it undergoes 3 rotations, it's in a different configuration. So let's try it like this. Okay, now in this configuration, what will happen is X is still going to be along this axis. So I'm just going to draw a triple dash here, indicating 3. And then Z is still going to be along this. And then X cross Y is Z, so Y is still going to be this. So this is my C3. So you would know the dimensions of the object or the orientation of the object in this frame. So once you know that, you put that there, you put in the 3 rotations, and then out will come what is the configuration of this object in frame 0, which means that my original frame Y is here, Z is like this, and then X is like this. So I just redrew this X, Y, Z like over here. What it's telling you is that if you give it the positions of the object in X triple prime, Y triple prime, Z triple prime, typically the orientation in that frame is going to be the length, width, and breadth, right? It's still going to be whatever the length is along the X prime axis, Y prime, Z prime axis. So in local frame, you know what the object looks like. It's going to be its dimension in local frame. So what it means is, so it's still X is this way. I draw Y, X bigger face, Z is along this, and Y. So along X, you can, if the origin is there, X is still going to be its length along that. It's going to be whatever its length is, L00, say, or LX00. Along Z is going to be 00 LZ, and then 0 LY0. Okay, so that's what it means to be in body frame. You know the position of that in body frame means you know its position along the X, Y, Z axis. And it's typically going to be something like 00 LZ, LX00. And so you put that, it's very easy to get that. And then when you put these transformations R, Z, Y, X, you will find what the X, Y, Z position is in this frame. Okay, so okay, so question: for our application of Euler angle rotation, should we worry about gimbal lock in 3D? Okay, so I am getting to gimbal lock in a bit. In our applications for legged systems, typically if the robot is walking like a human, right, not doing crazy things, then I don't think we need to worry about gimbal lock. So what is gimbal lock? Gimbal lock is something which happens when at certain configurations of Euler angles that there is a matrix which becomes not well defined. It basically becomes, if you take the invert, it basically boils down to, gives you an angular speed of infinity, just like a singular configuration. And we'll come to that when we talk about angular velocity. But as far as I know that we shouldn't worry about gimbal lock for legged systems. If the robot is doing a flip in 3D, maybe it's an issue. Gimbal lock is often a problem in space systems where things are tumbling and moving. So when there's no tumbling, you don't have to worry about gimbal lock. But I'll come to gimbal lock, so don't worry about that. Okay, so what I was saying was this C0 is going to give you what are the coordinates of this point in along x, y, z, say coordinates of this point along x, y, z, that is the global x, y, z, which I drew here, and same thing for the other face, right? And so only thing to remember is we did these 3 rotations in this order. We did z, y, x, and that's how you will write them. You will write first, the first rotation will come here first, the second one will come second, and the third one will come third. Okay, so if you reverse the order, so if you go instead of z, y, x, you go x, y, z, or Euler or the Bryant angles, then it will be rx times ry times rz. Okay. Okay, yeah, so there is another aspect of this called Quaternions, and I will not get into it, but there's another way to represent this, and it's actually not that hard to go to Quaternions, another way of representing rotations. Okay. Okay, so then if you want to see how this looks, if you do this multiplication rz, ry, rx psi, and I would never recommend doing this by hand. It comes out to be, and I did it by using MATLAB, it comes out something like this. I just want to show you the form because you've not seen what it looks like before. You only saw the simple case of rotation about one axis. Okay, so that is the first column. Okay, now second column, it's more complicated. Cos psi, sine phi, sine theta minus cos phi, cos psi, sorry, sine psi, cos psi, cos phi plus sine phi, sine psi, sine theta, cos theta, sine phi. Okay, that ends the second column. You can see it's complicated. And then the last one is sine psi, sine phi plus cos phi, cos psi, sine theta, cos phi, sine psi, sine theta minus cos psi, sine phi. Okay, and then cos phi, cos theta. Okay, so those are the 3 rows, 3 columns of the rotation matrix. Let me show you an animation and we'll take a break. My goal is to show you some rotation animations. Okay, so what I did was I basically made a box using 3D animations. So we've only seen 2D animations, but the way you do 3D animations, I may have hinted to this, is you need to use what is known as patch. It should be somewhere here. Okay, so this is actually a more complex code than using patch. I have to, so maybe I'll run this first and then I can tell you a little bit more about the animation. So I'm going to run this code. It basically shows what happens if you do, so it started, so this is the same thing I did on paper, right? I showed you 2 rotations, first about X, then about Y, and then about Y, then X, just to show you that they're not commutative. I start with the same configuration, then it undergoes rotation about the X-axis by 90 degrees. Sorry, this will be Y-axis about 90 degrees, so the Y remains unchanged, and then X about 90 degrees, and then the reverse rotation. So the main message is that that final configuration here, row 1, column 3 is not the same as row 2, column 3, even though we started the same configuration and did this rotation sets, because multiplication is matrix rotations is not commutative. Okay, so that's one thing. The other thing I want to show you was that how do you actually do this? You actually have to draw boxes. And the way I did it was I basically specified vertices of the box. So there are 8 vertices. I specified the faces of each of the vertices. Okay, and so face is given by 3 dots, right? 4 dots corresponding to the 4 corners of the face. And then I think I used patch. So I used patch, which I think I briefly, or maybe I gave you review videos to how to use patch. But I would just use this code again. If you want to draw a box, just use my code instead of trying to figure this out, all these combinations. But you can basically draw this. And then I use this utility called draw line. Somebody on MATLAB Central had shared it. Basically helps you to draw a line with an arrow, which is not there in MATLAB. And then 3 rotations you see here, Rx, Ry, Rz. So in this case, I'm just doing Rx times Ry for rotation XY. And then for the other one, rotation YX, I am rotating right here, the end, Ry times Rx. And then what else? I also have, I believe these are the formulas. Let me just run this. Okay, this is just illustrating rotation. So if you start with the initial configuration, then you do rotation about the z-axis, 90 degrees. So if you want to understand this, this code might be a good starting point. So 90 degrees about the z-axis, and you get this. The z-axis remain unchanged, then 90 degrees about the y-axis, and 90 degrees about the x-axis. So it's going 90, 90, 90 rotations about each of the axes. And so you can start off with this code and then get to that. So I think okay, that's it. So let's